Welcome students to the MOOCs course on fuzzy sets, arithmetic and logic. This is lecture number 25. If you remember, in the last lecture I said that in today's class I shall talk about inferencing from conditional propositions. Let us recall what we have done. In the last lecture, we have seen how to assign truth values to fuzzy propositions. In particular, we have talked about fuzzy propositions of two types. One is conditional, other is unconditional. Unconditional fuzzy propositions allowed us to transfer the uncertainty associated with the fuzzy terms to the truth value of the fuzzy proposition. So, that gave us the foundation for the work. On the other hand, in conditional, what we have done, we looked at statements of the form if x is a, then y is b. That is, we are drawing inference about y from x, and this can be done as x implies y. Now, inferencing about a variable from another variable is not new. For example, consider a function, say y is equal to f x. What is the advantage? If I give any value x for the variable capital X, then we know from the function what is going to be the value for y. In fact, we can go even further. Suppose we give an interval on x and I call it a, then we can see that the value of y is going to be in this set or in this interval. which we call B. Suppose we extend it to relations. Suppose we have the following. This is x, this is y, and there is relation for each x with several values of y's, and each y may be related to several values of x. So, let us assume that we get something like this. So, that corresponding to each x, we know what are the y values that are associated with. So, given x, now I can identify this set of values which are associated with x. On the other hand, if we consider say an interval x 1, x 2, then we can see that this is the set of values of y which are associated with this interval a on x. It does not mean that all y values in the interval b are associated with all values of x in the interval a, but we know that any y belonging to this interval b is associated with at least one x in this set A. Therefore, we can write the following. Chi b of y is equal to supremum over x belonging to say x minimum of chi a of x and chi r of x y. That is, whether y belongs to B or not depends upon one, if R x y, then x belongs to A or not, and 2, whether R x y exists or not. So, if both y is related to x and x belongs to A, then we see that y belongs to B. Although here we have used supremum, we know that all the chi values are either 0 or 1. So, when both of them are 1, then only we see that y belongs to B. Now, suppose we extend it further. And we have the following relation, a very similar type of drawing that I have drawn before. Suppose this gives us the relation of x y, and we want to find given x belonging to A, where A is an interval on this, what is B. Now, we make further generalization. Suppose this A is a fuzzy set and it has a membership value, say something like this. Then, as before, we know that this is the set B which is associated with x belonging to A, and our target is to find the membership function mu B y that describes the fuzzy set B. Or in other words, given the relation, so this is the relation that is given, these are the points which are associated with the corresponding x. We want to find out what is going to be the membership of an y belonging to this set or this interval B, when we are looking at that x implies y and we are focusing on the subset A of x, and we are trying to find out the membership of y to the fuzzy set B. So, how we proceed? We imitate the equation given for crisp sets, and we write mu B of y is equal to supremum over all x belonging to x, minimum of mu A x and mu r of x comma y. If you are confused, let me make it little bit more specific. For a particular y is equal to y naught, what we are looking at? We are looking at all those x which are related to y naught, and this relation is given by mu r, and all those x which belonging to A, and this is their membership. So, we look at the minimum of this. We are just imitating what we did with respect to crisp sets, and we can see that if we take the maximum or supremum of them, that gives us mu B of y naught. Now, mu A of x is given, or the fuzzy set A on capital X is already defined. And we want the membership of y in B. Question is, what is mu r x y? This comes from the implication. We know that Lukasiewicz has given the following. Truth value of A implies B is equal to minimum of 1 and 1 minus A plus B. Now, we are given the following conditional statement. If x is A, then y is B, where this is a fuzzy set. Therefore, we know mu A of x, and this is another fuzzy set, and we know mu B of y. Therefore, from this above implication, using Lukasiewicz, we get R, or say mu R of x y is equal to implication of mu A x and mu B y, and therefore, mu R x comma y is equal to minimum of 1 and 1 minus mu A x plus mu B y. Let me now illustrate with an example. Suppose we have the following. Conditional proposition. If temperature is cozy, then speed of fan is moderate. So, we can see that there are two fuzzy terms A and B, where A is temperature is cozy and B is with respect to the speed of fan, that the speed is moderate. Suppose we define cozy as the set 0.9 upon 25 plus 0.7 upon 30 plus 0.4 upon 35. Here 25, 30 and 35 are temperature in Celsius. Or in other words, we are saying that if the temperature is 25 degrees Celsius, then membership to cosinus is 0.9. Similarly, for 30 it is 0.7, for 35 it is 0.4. So, to keep it simple, we have taken discrete values. In practice, of course, one can take a continuous range of temperature and one can assign the membership values by defining appropriate function. In a similar way, suppose the fuzzy set moderate on speed of fan is defined as follows. It is 0.8 for a speed of 120 revolutions per minute or 0.3 for a speed of 200 revolutions. So, this is my set A and this is my set B, and we are given if temperature is cozy or in A, then speed is moderate, that is speed is B. Therefore, we can obtain the relation R as follows. R which is between x y, where x takes only 3 values 25, 30 and 35, and y belongs to the values 120 and 200. Therefore, mu r x y is defined as mu r of 25, 120 is equal to minimum of 1, 1 minus 0.9 plus 0.8 is equal to 0.9. Mu r of 25, 200 is equal to minimum of 1 and 1 minus 0.9 plus 0.4 is equal to plus 0.3, which is equal to 0.4. Mu r of 30, 120 is equal to minimum of 1 and 1 minus 0.7 plus 0.8 is equal to 1. Mu r of 30 comma 200 is equal to minimum of 1 and 1 minus 0.7 plus 0.3 is equal to 0.6. Mu r of 35 comma 120 is equal to minimum of 1 and 1 minus 0.4 plus 0.8 is equal to 1 and mu r of 35 comma 200 is equal to minimum of 1 comma 1 minus 0.4 plus 0.3 is equal to 0.9. Thus, we have the following relation matrix. Instead of the exact values, let me call them x 1, x 2, x 3, so that you get a generalized view y 1, y 2, and we have the following memberships 0.9, 0.4, 1 and 0.6, 1 and 0.9. Further, we have the membership of for the fuzzy set A, and which is given as 0.9 for x 1 plus 0.7 for x 2 plus 0.4 for x 3. Note that x 1 is equal to 25, x 2 is equal to 30 and x 3 is equal to 35 and y 1 is equal to 120 and y 2 is equal to 200. So, question is, what we can infer from here? So, let us look at the following. In propositional logic, we talked about modus ponens, modus tollens and hypothetical syllogism. So, these three tautologies allowed us to infer about a variable given some facts and some implication. So, when we are talking about fuzzy, we want to generalize this concept of modus ponens, modus tollens and hypothetical syllogism. So, for fuzzy inference, we generalize the above three tautologies. So, let me explain them. Consider generalized modus ponens, let us recall modus ponens says that A and A implies B implies B. What does it mean? It means that if A is true and A implies B is true, then together they imply that B is true. What happens in case of fuzzy? We are given if x is A, then y is B, or we can write it as A implies B. Now, suppose we are given x is A prime, that means x comes from a different fuzzy set A prime defined on the same set X. Therefore, our aim is to infer about a fuzzy set B prime defined on same Y, given A prime and A implies B. So, with respect to the above example, suppose we are given x is A prime, where A prime is defined as (0.2) for 25 plus 0.6 for 30 and 0.9 for 35. If you remember, we are calling them x 1, x 2 and x 3. Therefore, our aim is to obtain B prime, that is mu B prime for y 1 and mu B prime for y 2, where we already have these two relations. This is x and this is r. So, what we do? We do the following: mu B prime of y 1, which is actually 120 revolutions, is equal to maximum over x minimum over mu A x, mu A prime x and mu r x y. Since A prime is equal to 0.2 x 1 plus 0.6 x 2 plus 0.9 x 3. Therefore, what we write? Mu B prime of y 1 is equal to maximum of minimum of mu A prime x 1 and mu r x 1 comma y 1, minimum of mu A prime x 2 comma mu r x 2 comma y 1 and minimum of mu A prime x 3 and mu r of x 3 y 1 is equal to maximum of minimum of 0.2 and 0.9, minimum of 0.6 and 1 and minimum of 0.9 and 1 is equal to maximum of 0.2, 0.6, 0.9 is equal to 0.9. In a similar way, mu B prime of y 2, which we know that is equal to 200, is equal to maximum of minimum of 0.2 comma 0.4, minimum of 0.6 and 0.6 and minimum of 0.9 and 0.9. So, the first one is coming from this set and the second one is coming from this matrix R. So, this is equal to maximum of 0.2, 0.6 and 0.9 is equal to 0.9. Therefore, we infer that if x is a prime, then y is b prime, where b prime is equal to 0.9 for y 1 and 0.9 for y 2, where y 1 is 120 and y 2 is 200. Let us now look at generalized modus tollens. So, let us recall modus tollens says that if A implies B and not B, then not A. That is, not B and A implies B implies not A. That is, if we are given the implication and we are also given that some information about B, then we can derive some information about A. Let us now look at in case of fuzzy sets. So, with respect to the same example, suppose we are given B prime is equal to 0.4 for y 1 and 0.9 for y 2, and we are given A implies B, from which we got the R. What was that R? Just for your recollection, it is 0.911, 0.4, 0.6 and 0.9 for x 1, x 2, x 3 and y 1, y 2. Therefore, mu A prime of x naught or any x, we can write it as maximum over y minimum of mu B prime y and mu r x comma y. Therefore, we get the following: mu A prime of x 1 is equal to maximum of minimum of 0.4 and 0.9, comma minimum of 0.9 and 0.4. Why it is coming? So, let us look at this. So, we are looking for membership of x 1 to a prime. So, you are looking at the membership of y 1 and the strength of relationship between x 1 and y 1 and the membership of y 2 and the strength of relationship between x 1 and y 2. So, you are looking at the minimum of this and the minimum of this and this, and we are taking the maximum of that one. So, we got 0.4 and 0.9, we are taking the minimum of that, 0.9 and 0.4, we are taking the minimum of that. So, what we get is maximum of 0.4 and 0.4 is equal to 0.4. In a similar way, mu a prime of x 2 is going to be maximum of minimum of 0.4 and 1 and minimum of 0.9 and 0.6 is equal to maximum of 0.4 and 0.6 is equal to 0.6. And finally, mu a prime of x 3 is equal to maximum of minimum of 0.4 and 1 and minimum of 0.9 and 0.9 is equal to maximum of 0.4 and 0.9 is equal to 0.9. Thus, we infer about a prime is equal to the set 0.4 for x 1 plus 0.6 for x 2 plus 0.9 for x 3, where this is 25 degree, this is 30 degree and this is 35 degree. Next, let us look at generalized hypothetical syllogism. It says that with respect to propositional logic, if A implies B and B implies C, then A implies C. So, what is going to happen for fuzzy relations? If R 1 is a relationship between x comma y and R2 is a relationship between y comma z, then we can obtain the relationship between x and z, let us call it R3, or in other words, given these two relations, we get the relation between the variables x and z. And the formula for this is mu R3 of x z is equal to, again, maximum of y, minimum of mu R1 x comma y and mu R2 y comma z. That is, we are looking at the strength of relationship between x and y and z. Therefore, for all possible values of y, we are looking at this relationship and we are looking at the minimum of that one. Then finally, we take the maximum of all these values. So, for illustration, we already had R1 is equal to 0.9, 0.4, 1, 0.6 and 1, 0.9. And suppose R2 is equal to y1, y2, 0.8, 0.3, 0.2 and 0.9. As you know, this is x1, x2, x3 and this is y1, y2. So, from these two we want R3 between x comma z, which is going to be basically the strength of relationship between x1 z1, x1 z2, x2 z1, x2 z2 and x3 z1, x3 z3. So, we do it in a very straightforward way. So, we take the matrix 0.9, 0.4, 1, 0.6 and 1, 0.9 and we composed it with R2, which is given as 0.8, 0.3, 0.2 and 0.9 and we imitate something like matrix multiplication. So, we take this pair, their minimum is 0.8, we take this pair, their minimum is 0.2 and so if we take the maximum of that, we are going to get 0.8. In a similar way, minimum of these two is 0.3 and minimum of these two is 0.4. So, if we take the maximum of that, we get 0.4. Similarly, minimum here is 0.8, minimum here is 0.2. Therefore, what we are getting is maximum is 0.8, 0.3 and 0.6. So, maximum is 0.6, 0.8, and 0.2, maximum is 0.8, and 0.3 and 0.9, maximum is 0.9. Therefore, we get this is the strength of relationship between x 1, x 2, x 3 and z 1, z 2. Thus, hypothetical syllogism allows us to infer about z given R between x and y and R 2 between y and z. Okay, friends, I stop here today, but before I stop, let me tell you that in practice the conditions can be more complicated. For example, say with respect to washing machine, one can say if the cloth material is heavy or the quantity of dirt is high, then speed of spin is very high. Thus, we get a disjunction of two clauses which imply the value of the variable speed of spin. In a similar way, it can be conjunctive, say with respect to medicine. If fever is high, and shivering is say fairly high, then check temperature frequently. So, this is a fuzzy term, this is a fuzzy term with a linguistic hedge, and we have a conjunction of these two clauses which imply this fuzzy term frequently. We know how to handle or and, that is conjunctions and disjunctions, and therefore, given the background that we have discussed today, we know how to compute the membership values for this, and from there how to get the implication relationship, and from there depending upon the problem we can use generalized modus ponens or modus tollens or hypothetical syllogism to infer about some other variables. Okay, students, I stop here today. In the next class, I shall continue with inferencing with conditional and qualified propositions, and after that we shall look into fuzzy quantifiers and how we can infer from fuzzy quantified propositions. Till then, thank you all.